What if a drone could identify and spray only weeds? You'd spray far fewer chemicals, which would save you money. You could also stop using implement sprayers that compact your soil, all while maintaining yields. I've built just such a drone using off-the-shelf components and free and open source software to fly the drone, classify images, and spray only weeds. Big Ag's just getting into this. John Deere has a smart sprayer for $250,000, and there's a laser weeder tractor that'll burn your weeds for $1 million. But those prices are out of reach for all but very large farms. In this video, I'll show you how to build this smart, autonomous sprayer drone for $1,000. I'm Nathan. I had a field full of prairie grass that was being overtaken by blackberries, so I decided to do something about it. I built a drone, added a camera, and a sprayer with nozzles, and with the help of a bit of machine learning, that is, image classification, I was able to identify and spray only the blackberries. It worked surprisingly well, and I think this project could be much more widely used. Let's start with an overview. This is a standard drone frame. It's an S500 frame, standard motors, standard props. There is a bill of materials, that's all the parts used to build this thing, listed in the description below. And there's an electronic schematic for how this is all connected together. There's 3 places on this thing where we get a bit of magic that's outside of the norm for a drone. The first one is this orange thing right here. This is the autopilot. It's built on a project called ArduPilot. It, combined with the GPS unit right here and the downward facing LiDAR right here, help this drone fly on a defined path over our fields at about 6 feet off the ground, which makes it excellent for spraying. The second place where we get some magic is this camera right here. This is just a normal drone camera, and it's sending images back to our base station. That's just a laptop. On that base station, we're running Tensor Flow. Think image recognition software. That way we can decide if what we're looking at is a blackberry or prairie grass. Now, I mixed a little bit of extra magic in here. I actually used images taken by this drone and classified them myself into weeds versus prairie grass, which significantly increased the reliability of my model in detecting things in my field. Think of it like a special course that you use to train up your machine learning model to identify things in your field. Using this very primitive and inexpensive hardware, we can still get excellent results when we train up our own model like that. And it's surprisingly easy to do. So I'll show you how to do that a bit later in the video. Also, I'm currently reworking this camera right here. You can get some really unreliable video transmission back to your base station, and we can do significantly better if we use an onboard tiny computer and an onboard camera. That's going to come out a bit later this summer, but this system worked last summer, so I'm going to show you how it works here, and we can make upgrades later. The third place where we get a bit of magic is down here. This is landing gear and a tank. This is just hollow PVC all the way around, and it can hold liquid. This right here is a tiny pump, and down here we've got 2 sprayer nozzles connected to that pump. So whenever our base station determines that what we're looking at is a weed, it sends a signal out here, this pump turns on, and we can spray whatever's in this tank right here on whatever we're passing over with the drone. Here's a quick demo of how all these systems work together. First, the base station, that's just a Windows laptop, it calls up Mission Planner and it connects to the drone. Then it connects to the base station network here in Iowa. That's so we get a much more precise location for our drone as it flies over the fields. Next, it loads up a mission that tells the drone where to fly over the fields, and it starts up the drone camera. Then it starts up an interconnect between the base station and the drone sprayer, and sends the drone out on a mission. The drone uses its GPS and LiDAR to follow the planned route, hovering about 6 feet over the ground, following the contours of the ground as well. The camera takes a photo every second and sends it back to the base station. Tensor Flow identifies the content of the photo and decides if it represents a weed. If it does think it's a weed, it turns on the sprayer for about 1 second. The drone completes its mission and returns to the starting point to land. Each mission only lasts about 10 minutes before the battery is depleted, so clearly it would be nice to automatically land, battery swap for a charged battery, and start the next spraying route so you don't have to handle those tasks every few minutes. I built just such a landing pad and battery swap station, seen here, and I'll give you a link to that video, or check the description below for a link to that video. Now let's move on to the drone build. Let's dive into the details of how to assemble this drone. First off, you're going to start with a frame. This is an S500 frame. You could go a size or 2 larger than that if you'd like. follow the instructions that come with your frame to screw it all together. You can see that there's little screws here, here, etc. Just follow the kit instructions to assemble that, including the landing gear down here. Next, you're going to add your motors and your electronic speed controllers right down here. So each of these arms has a motor screwed on like this, and then an electronic speed controller right here. There's just little banana plugs that plug from the motor into the speed controller on this side, and then out the other side of the speed controller come a big red and black wire. Now you will have to solder that big red and black wire right in here so that you can get it connected to the power supply that runs through all of this printed circuit board. You'll also have a control wire coming out of those, which you'll plug into your autopilot in just a moment. But for now, just get your motors and your ESCs on. One extra note on these electronic speed controllers: don't worry about the order of these wires that you plug in here just yet. Get them plugged in and we'll test that in a bit later. When we actually fire this thing up, we'll do an ESC calibration test and a motor test. And those two are important. They'll help you get the ESCs calibrated in the first instance, and then make sure that these are plugged correctly and have the right direction in the second instance. All of these props should spin inwards, 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 and inwards on the ends, the front and back end of this. And so when you do that motor test, you can see if those are spinning the right direction. If they aren't spinning the right direction, swap any two wires that plug from the motor to the ESC, and it should reverse that direction and get you spinning the right way. Next set of pieces to assemble here are our autopilot. Now this autopilot actually comes with its own power supply. The power supply plugs into it right here. But that power supply does draw from the same plus and minus that the rest of these draw from. So wherever you have these ESCs plugged in, you're also going to solder on the power supply that comes with this, and then connect the output of that power supply right into your autopilot here. So now that you've got the cube orange installed, use some of the sticky tape and foam that comes with it to fix it anywhere on the top of this drone. Next, you're going to want to install your GPS unit. You can screw it anywhere onto this printed circuit board down here. Make sure that you know which direction this little arrow is facing. That's going to be what faces this forward, and you are going to have the camera in the front of the drone, same direction that your GPS is facing. In the back here's where your LiDAR is going to go, just so you have enough space to fit everything in. This GPS has its own port, and it plugs in to your autopilot in the CAN 1 port right here. The next thing you're going to want to work on is your radio. This is just a 900 megahertz radio. There's a similar looking radio that plugs into the USB port of your laptop. So your laptop is your base station, and that's how it communicates with this thing. This has another port that comes around here, and it plugs into telemetry 1 port here. The last piece of equipment that's going to plug into your autopilot is the LiDAR. This is a TF Mini. You can see it's got two little eyeballs, and we have them facing down and velcroed onto these couple posts that come out of our frame here. That's so that it can see directly down to the ground, and it can keep this thing a consistent distance off the ground, as well as follow terrain. So any hills that you have, it'll follow those hills at say 6 feet above the ground. It plugs in to the GPS 2 port right here, just because it's easier than using a different I2C port. Now there is one special note here. You see, this wire coming off of here does not have a socket that will plug into your cube GPS autopilot. So instead, you're going to take what would have been the GPS 2 cable. There's lots and lots of cables that come with this cube orange, and you're going to adapt it to connect to this TF Luna. Pins 1, 2, and 3 connect up just like normal, so solder those together. But then, pin 6 of your GPS 2, that is the pin all the way to this side, the red pin being 1, this black pin on this side being 6, needs to be soldered to pin 4 of your TF Mini. That's the only way to get that TF Mini working on a serial port like GPS 2. Next, you're going to install your first-person viewer camera and your transmitter, which transmits video over 5.8 gigahertz back to your base station, which is your laptop. There you'll process those images. This is just a first-person viewer camera. It's pointed down and slightly angled so that it's looking at things that are 1 to 2 meters in front of the drone. There's one wire that goes in between these two. It's this yellow wire right here. It's the video pin coming off of here, and it gets soldered to the video pin of your transmitter right over here. These also get power. This gets a 5-volt power supply, and this gets a 10-volt power supply. More on that in just a moment. This transmitter right here, through a long wire, heads over to this radio right here. I've just hidden it so that it's out of the way, won't get hit by any props, but this is what actually sends 5.8 gigahertz video back to your base station and is received at the base station. All of these transmitters have different ways to configure them. Set them at the highest power setting, and as long as you don't have a lot of other 5.8 gigahertz traffic around you, you should have no trouble picking it up at your laptop. So, these also have a 5-volt and a 10-volt power supply. Where does that come from? If we flip the drone over, we see that down here we have this chip right here. Here is ground and 5 volts, ground and 10 volts. So this has a ground 5 volt and video, this has ground 10 volt and video, and then this wire right here sending out for the antenna. Those are the only used pins on these. The rest of them can just be tied off. They're unused. Next is the tank, pump, and sprayers. As you can see here, I took the downward facing legs of my drone, and rather than using the landing gear that came with the kit, I siliconed these 1/2-inch PVC pipes to those legs, and then I continued to use 1/2-inch PVC right angles and T's all the way around. What does this do? Well, this is just a hollow piece of PVC that connects all the way around my landing gear, so it can be filled up with liquid. I use silicone in all of these joints so I can pull it apart if I need to, rather than chemically bonding these together with the usual PVC bond materials, but it does hold water just fine. Over here, I put an overflow tube on. This distance right here is slightly smaller than this distance right here. So when I go to fill this up, I can fill as much as I like, and I know that it will eventually pour out of the overflow tube over here. That way I end up with a completely full tank without worrying about exactly what's in there. Next, I have this 1/4-inch inside diameter tube. It's reaching all the way down inside the tank there, and it connects to the inlet valve of this pump right here. The output valve of this pump is velcroed across here to keep it stable, and it connects up via that same 1/4-inch inside diameter tubing to a nozzle. This nozzle right here is used in a mister system. The last thing to note is this rather strange looking battery bay. You can use the battery bay that comes with your S500 frame. I chose to modify it. I just took my battery, put balsa wood around the outside, zip tied that in place, and then glued all of these pieces together. Why did I do that? It's because I have copper tape right in here, and that copper tape extends through the frame out to here, and then is soldered through these wires to the plus and minus on my circuit board for my S500 frame that distributes that battery voltage out through everything in the drone. The reason that I did that is because I also have specially modified batteries that I can just slide in there and provide power for this. If you want to learn more about that, have a look at the video in the description. I have an automatic battery swap system for this so that I don't have to be around to refill the tank and swap the batteries. This thing can continually run missions while I am not present. On to part 2, which is the base station setup. That's our Windows laptop and our first drone flight. There's 3 pages to look at here. The first is from autopilot setup. The second is from autopilot, the first flight with copter. And the third is from the Here 3 Plus GPS page, which shows how to integrate it with our Cube Orange. So read through those, and then we'll move on. Connect your Cube Orange to your laptop via a USB cable, and then install Mission Planner from the download page on Mission Planner. Open Mission Planner and go to the Setup tab. Click Install Firmware and install the latest firmware for your copter, that is the X-shaped copter, on your Cube Orange. Remove the USB cable from your Cube Orange. We're going to connect to it with the 900 megahertz radio instead now. So connect the battery to your drone to power it up, and then plug your 900 megahertz radio into your laptop via the USB port. You may have to install some drivers for the 900 megahertz radio via USB or read up on autopilot pages about configuration, but for me, I didn't do any of that. Windows grabbed the drivers, and as soon as I clicked the connect button in Mission Planner, it auto-connected to the drone. No configuration required. Now we're going to get into the guts of Mission Planner to configure this so it'll fly from our base station instead of having us control it with a controller in our hands. Flip over to the Config tab and go to the full parameter list. We'll start by looking at the arming check. Just double click on the value and you'll get this bit mask that pops up. I've chosen the bare minimum. This means that I'll look for a barometer, compass, and GPS lock before I'm allowed to arm my drone. You probably should include board voltage, battery level, and rangefinder in yours as well. But some of these others can get in your way, especially since we don't have an RC connection to control it ourselves. We aren't going to be able to have those as part of our pre-arm check. The next thing to look at is the auto options. Again, double click, and this is what we're allowed to, what we are allowed to do from the auto mode. We're always going to fly from auto mode since that's where we can run an automatic mission. We're going to allow arming and allow takeoff without raising the throttle. The next setting, avoid enable, set to 0, is actually the default. I had to keep it that way because I got into trouble when I had set avoid enable to other things. Board safety enable is set to 0 because we don't actually have a safety switch plugged into our cube orange. So please set that to 0 so that you don't get into trouble not having that plugged in. The next 4 parameters are can underscore D1 and D2. These settings all came from the Here 3 and cube orange configuration page. So we've just set them the way that that page says we should have it set up so that our Here 3 GPS can talk to our cube orange. FS underscore throttle underscore enable is set to 0. I was unable to power up the drone when I had that set to a non-zero value. The GPS type is set to 9 and the NFT LED types are 231. Again, taken from the Here 3 and cube orange manual page. So those are just dropped in so that those will work properly together. After those, we come along a bunch of settings for our rangefinder. That is our LiDAR, which is downward facing. So this is getting the TF Mini to work properly. So all of the rangefind 1 underscore are settings for distance. So it's 5 centimeters off the ground. It can see for 1,000 centimeters out. It has a minimum vision range of 10 centimeters. Its orientation is 25, which is facing the ground. And the rangefinder type is 19. That is a Bennewick TF, which is the series that we have. Serial 4 baud and protocol set to 115 and 9 just mean that GPS 2, which is serial port 4 on that board, is used to communicate with it at 115 baud. So those are just settings that we took if you want to go read about them there in the autopilot forums when you look at TF LiDARs. That's all of the hidden parameters we're going to look at. Everything else will be done here through the GUI. Next, go to Config tab, Flight Modes, and set all of them to auto. This is so we can always be in auto mode no matter what flight mode it thinks we could possibly go to. This is because we don't have a remote control in our hands, so we always want to fly out of auto mode. Pop over to the Setup tab under the Mandatory Hardware and look at your frame type. It should be an X type. Under our initial parameter setup, we've got the battery voltage and the type of battery that we have here. We're going to probably be using a 4S LiPo battery, and those voltages are pretty normal for a 4S LiPo battery. Next, go to the Acceleration Calibration tab and do each of the calibration tests. This will have you set your drone forward, back, side, etc. It's so your cube orange and GPS can get all of their calibrations correct. Next, go to the Compass tab and be sure that you have your UAV CAN compass as the top priority and that you use compass number 1. That's using your Here 3 Plus compass so that it's the one that actually gets used for all this calibration. You're going to have to click the Start for onboard mag calibration and basically swing your drone in a 360 arc in every orientation possible. When it's finished going through every orientation possible, you'll actually get a little green complete, and then it'll ask you to reboot your drone, which basically means remove the battery and put the battery back in. You can skip the radio calibration tab since we don't have a radio controller in our hands. That's where you would configure it and make sure that it's got all the proper settings. The servo output should be standard. Motor 1, 2, 3, and 4 are all set with a minimum and maximum PWM and a trim PWM, which is the setting that they have when they're idling. You should calibrate your ESCs. This should be an automatic process. You can see what's shown here. And when you click Calibrate ESCs, it'll go through a process on your drone, and then it'll ask you to reboot the drone. When that's finished, all of the ESCs should automatically have the right settings, and that would show up in your servo output tab as well. On the failsafe tab, we want to be sure that we set the correct low battery voltage so that we do call this thing back when it reaches a low enough battery. Remember that you connected the power supply for the cube orange as a pass-through, so the battery voltage passes through that on its way to the power distribution board. That way, the cube orange can actually sense the voltage of the battery as well as how much current has gone through there. We'll get to a different tab a bit later where we actually configure the behavior for that. Next, we establish base station corrections on the RTK GPS Inject tab. Now here in Iowa, we have the Leica network, which is a network of base stations that are set up for farmers to use in their combines, tractors, etc., and we can use it here as well. The way that we do that is over an internet connection. You see we have this set up for an N-trip connection in the top there. We click the connect button and it prompts us to enter our remote host information. I'll flash the format of a remote host. So if you have something like this in your state, you should absolutely sign up for it, figure out how to connect over the internet just like this, and you'll be able to use base station corrections on your Here 3 GPS automatically. If you don't have something like this, you don't live in an agricultural state, for example, you're going to have to buy the Here 3 base station and follow the instructions on that website that I showed you earlier to set that up and use it. But in my case, this is fairly simple. I connect to the base station over the internet. My drone starts sending back its base station information that it's receiving, and then I'm able to pass it over the 900 megahertz connection information about how to correct its GPS position. This is where we get RTK float or RTK fixed position. If you wait long enough, you'll actually get RTK fixed position. You can see those things if you flip over to your data tab. It'll show RTK fixed there. This is the battery monitor tab, and it's useful because you're going to set up the behavior if your battery gets low here. So you need to tell it first off, you've got a cube orange and you want it to look at the analog voltage only. You can also have it determine how much current has passed through the current sensor of your power module, and in either case, if you're using analog voltage or current, you can go back to that fail-safe tab that we were on earlier and set the behavior for it there. And what this will do is if it notices that that analog voltage is getting low or the battery capacity is getting low, you've used up enough amps that you're depleting your battery, it will call the drone back from wherever it is on its mission and have it land at its home point. So a little bit later when we're setting up the missions, you need to set the home point, and that's where it's going to try to land. So this is a fail-safe for if things are going badly. The rangefinder tab is where you can ensure that your TF Mini is operating properly. So what this shows is the distance from the TF Mini to the ground currently, what it thinks anyway. And if you actually pick up your drone, so move it around so that LiDAR is pointing at different surfaces, you should actually see the distance value on here change. You can see that's exactly what I'm doing here, changing the distance values by moving the drone around and then setting it back on the ground. One other note here, you can use a second rangefinder to do object avoidance. You recall back in the settings when we were going through the detailed name settings, one of them was called avoid enable. And if you have a forward-facing LiDAR set up somewhere else, you can turn on avoid enable and your drone will automatically stop when it senses that LiDAR is approaching whatever value you told it to avoid, and it will try to go around whatever obstacle it sees. We're assuming that we can set up launch files and mission files that avoid all obstacles, so I didn't put in a forward-facing LiDAR on this thing. Next is the motor test tab. This is super useful. I always run the throttle at 5% and the duration at 2 seconds, and I go click on test all motors in sequence. So what that does is it works its way around the drone motors and it spins each one of them at 5% capacity. So it's not going to take off. But that's a really easy way to see if you've got everything configured properly for your motors, that your ESCs are working properly. Each prop should spin slowly, and as we showed in the introduction section where we were assembling the drone, the front and back of the drone, each prop should spin inwards toward the front or the back of the drone. That's all of the things that we're going to look up in the Setup tab. Next, we're going to plan a mission. Popping over to the Planning tab of Mission Planner, we have a sample waypoints file here. What is this? Well, it's actually just a text file. You can create it using a text editor, or you can open up this tab right here, zoom in on the satellite image of your property, and start clicking, and each time you click, you'll drop a waypoint. You can set commands and other parameters about each one of those waypoints. So let's take a little bit closer look at what we've got going on here. First off, you see the first command is to take off, and you can tell that it goes to an altitude of 2. That's 2 meters off the ground. We want to keep this thing nice and low, not go super high up in the air. And the next thing to note is the terrain setting. What that means is use the LiDAR. If you say relative, it's going to use a barometer to determine its altitude. If you say terrain, it means use the LiDAR to figure out how high up you are off the ground. A couple other things to note, our waypoint radius is intentionally small, 0.05, which means be precise. Hit these waypoints right on the nose, don't be within 2 meters. Taking a look at the second command here, we do change speed, that there's no location set for that, but what that means is make the drone go 1.5 meters per second. You see that tab where it's set. That's essentially slow. We want to go slowly over here so that we have time to spray things rather than racing through our field. The next waypoint is actually identical to number 1. It's the same location, and it means sit here. It's unnecessary to hit that, but I wanted to show that we have that waypoint in there. After that, we have waypoints 4 through 6. Those are just saying to this drone, fly on a grid pattern over the field. This happens to be a part of the field that's got lots of blackberries in it, so it's very good to fly over it. So every one of those waypoints just means follow this path as you work your way through the field. When you get to waypoint 10, it sends it back to waypoint 11, which is very close to where it took off. There's actually a bunch of waypoints that are buried right over that home location. You may only see number 13 there. Waypoint 11 is intentionally close to there. It sends it sort of on a landing route, if you will, like an approach to the landing pad. And then waypoint 12 is actually located right where waypoint 1, 2, and 3 were. And then our landing is right where waypoint 12 was. So what that says to this thing is spend your whole flight at altitude of 2, 6 feet off the ground, 2 meters off the ground, 6 feet off the ground. And then when you make your way to the end of this waypoints file, land exactly where you took off. And the reason for that is I actually have a landing pad set there, and when it lands where it took off, within a few centimeters of where it used to be, or even a meter or so if it gets gusted by wind, that landing pad will automatically swap out the battery and refill everything for me, so I don't have to be present, and it can just take off on its next mission. So it's important for me to have 11, 12, and 13, those waypoints that are identical every time. It sets the drone on a known path, so it's a known orientation when it lands on the landing pad, and it lands in the exact same place that it took off each time. Now let's dive into what this waypoints file actually looks like. This is a text file I mentioned, but I've pulled it up here in sort of an Excel editor so that you can see the columns and rows of this thing. And let's compare it to what we were just looking at in the waypoints tab of Mission Planner, or sorry, the planning tab of Mission Planner. First thing to note is there's a row 0, which is the home location. That was not shown to us before in the planning tab, but you want that to be exactly the same as your first waypoint and your landing waypoints. Next, you see I made some notes along the side. These are not actually present in the real file. I just added them here for your benefit. You can see that waypoint 1 and waypoint 3 have the same location as the home tab, and waypoints 12 and 13, that is the last waypoint and the landing, have the same location as the home tab. Now in column column D, you can see that we actually have different numbers appearing. That sets different commands. So number 16 is the home command. Number 22, the next one there, is the takeoff command. Number 178 is do change speed, and then there's a bunch of 16s after that in column D. Those are all the waypoints that we're going to go. And the very last one, 21, is land. You can also see the height up off the ground for all of these. That's listed in column K. So all of those 2's in there means stay 2 meters off the ground regardless of where you are. So that's all. A waypoints file is just a bunch of text, honestly, and you can create them any way you like, but prepare a bunch of them so that you can fly over your field in about 10-minute bursts before you run out of batteries and reach all the places that you want to reach. That was a lot of preparation. But now, assuming that you've done all of those steps, you can flip over to the Flight tab, click Auto, and then click Arm, and your drone should take off and follow the first mission that you wrote to it. Great job. Your drone is flying. Now it's time for part 3. Collect some images from that drone and start processing those images. The first step is to install Python. I'm using Windows here, so I'm going to install 3.10.10. You have to run 3.10 for Tensor Flow to work properly. Next, you're going to install Tensor Flow. Tensor Flow is the actual machine learning processing that sits on top of the Python programming language. Go to the Tensor Flow official page for your operating system and follow all the steps there. We aren't going to be doing TensorFlow processing on GPUs, so you can skip the steps where it's specific to setting up TensorFlow for a GPU and just follow things for the CPU environment. Open up the idle shell IDE, which is just a nice way to run and edit Python programs. And take a look at the various programs that I've got here. This is a step-by-step way to ensure that your camera is working and then build your own model and eventually run that model. The first program we're going to run just makes sure that the camera on our drone actually works. What it does is opens up a video capture, either a 0 or a 1 goes in here. Your webcam may be a number 0, and then the USB that you plug in to receive the camera signals from your drone might be a 1. Experiment with both a 0 and a 1 here until you find the one that works. Be sure you have your USB plugged into the side of your laptop, and you power up your drone and the camera and transmitter on your drone. Then run this program, and it should pop up a screen of whatever your drone is looking at. Let's see that same sequence of testing the camera from outside the laptop. So this is the receiver, and I click the button there, which actually tells it to tune through all the channels that it's got and find the whatever channel the transmitter is using. There's a range of bands that it can use. So that makes sure that it's actually tuned in to the transmitter on the drone. We can finally capture images from our drone. It's time to put that to use. This is the next program, and all this does is capture photos from our drone 1 frame per second and put it in a folder. That way we can sort through those photos later and put them into categories, a weed, a crop, something that, like our lawn or a building, and then we can use those photos to train a new model so that we have a model that will be customized for our place and the kind of crops and weeds that we have. And even with this cruddy hardware, we can get really good results identifying things because it's specific to where we live. So the things to look at in this code are the list. There's a weed list. It says weed, grass, and or lawn and crop. You can change that list to anything you want, and what's going to happen is those categories will be created. Literally, folders on your on your computer will be created with whatever those names are. And then we need to make sure that the camera is the correct number, 0 or 1. In that last webcam capture program that we looked at, we had to set a 0 or 1 so that we actually got the USB camera plugged in. That's really all there is to this. Make sure that you got the right number there. There's a whole bunch of commented out stuff in this. It's actually later on it will use the model that we create to classify things, but for now all that's commented out. So you need to get your drone and you need to get it ready to fly over your fields. Then you need to turn this program on, make it run, and it's going to create the directories that you said out in IA_predict. It'll actually create a run directory under there, a numbered one, so 1, 2, 3, 4, 5. It'll just make the next directory, whatever the last one was. If it was 5, it'll create a new one called 6. It'll create all the directories, weed, crop, lawn in there, and then it'll start taking snapshots from your drone, 1 per second, and it'll just drop those photos out into your directories there in the unknown, since it doesn't know what any of these things are yet. So let this thing run, let the drone fly over your field and capture a whole bunch of images, and then when you're all done with that, go and look at those images and start sorting them. So no longer in the unknown folder, put them into the weeds or the crop directory. That way we can later use those to train up a model. And the next step is to train up that model. So once you've got those sorted, drop them into the IA_photos directory. We're going to take a look inside these directories here. You can see these are examples of crop photos. The next is pictures of the lawn, and then pictures of weeds, etc. What you want to do here is put them in there because that's where we will build the model from. So IA_photos is where the model gets built from. Next, we need to jump over to the actual script that we use to build our model. So here is that build model Python script. There's not a whole lot of stuff that you can change about this. All it does is go out to our data directory, that's the ia_photos, look at the categories we've created, and then divide that training set of photos into a training set and a validation set. And then it iterates. It goes like 60 times or something like that through the training set and slowly gets better at identifying each of the photos and then checks itself against the validation set. At the end of all of that, it'll spit this out into the ia_model directory. I'm highlighting that right now. It's just a bunch of files that TensorFlow can then later use as a custom model to run against what's coming in from the drone. It's going to take hours to run. I have an underpowered laptop, and this takes 12 hours or something to run. But you will eventually get a model at the end of all of this. Then the next step is make sure that we can use that model just on a couple sample photos that we give it. So here I am actually running that script. You can see it's got epic 1 through 10. I think it goes through 6 epics before it actually spits out a model. Next, let's test our model ourselves. We go over to this predictimage.python, and all it is it's we're gonna give it a couple sample images in a directory out here, and we're gonna see if it does a good job classifying those. Now you do have to name each of these with cap_star. That's capture _star. Just grabs all of them. So throw a couple sample pictures from your drone out there and name them cap_1, 2, 3, whatever. And then run this script against it, and it's gonna pop up what it thinks each of these is and its percentage of confidence in that prediction. As an example, here are 3 photos. In the top left is a crop photo. Top right is a weed photo. You can see it's much more spotty and different heights of the plants there. But then in the middle is a sort of unclear photo. It's got a lot of distortion coming in from the transmitter on the drone, and amazingly, we're still going to be able to determine that those are weeds. Running that program, you can see this first image is a crop with a very high confidence interval. The next one's a weed, again with a high confidence interval. Even when we get to the distorted image, it's still a fairly high confidence that that is the correct identification. And these are very poor images. I mean, look at them. It's hard to tell what's going on. This is why, 2 things. One, it's really good to get more and more and more images to train up your model. It'll get better and better. And then second, we can significantly improve our identification by having a better camera and onboard processing. If we don't have to transmit these things over a wireless link, and we can just do onboard processing with a Raspberry Pi, we're going to get way better results out of this. So we should absolutely use this if we have to, but as soon as Raspberry Pi 0, 2 are available, that's going to be the right path to upgrade and get better image processing. I've got that in the bill of materials down below, and I recommend going that route instead. I'll update this video as soon as I have it done. Now's the time to put all this together. Pull up your sprayer loop Python script and let's have a look at it. This is what we're actually going to use when we're running the drone over the field to spray things. First thing to note, it loads the model. That's the model that we just created and that we just used in our prediction. Second, it's going to go create a new run directory out in ia_predict and drop everything out there. Third, it's going to take a snapshot every second, just continually from our drone's camera, and then it's going to process that image. It actually breaks it into pieces so that it can try to classify different parts of the image. And then this is the new part. It's actually going to try to classify those images. It's important to note that it's going to use a confidence interval. So I've got that highlighted there. If it's 70% confident that it's right, then it will drop the picture into the correct folder. If it doesn't have a 70% confidence interval, it's going to say, I don't know what this is. I'll put it in the unknown folder. So going out and actually looking at one of these folders, you can see in the crop directory here, we've got some pretty bad looking images, but those it thinks are, just grasses. And then in the weed directory, we've got a bunch of things that clearly do look like weeds. It turned on the sprayer for those. And then here in the unknown directory, if you get really bad video transmission, it just doesn't know what to do with it. And it will call it unknown. It won't turn on the sprayer. It'll just leave it out there and you can process those things later. If you can figure out what it is, go ahead and put it in a folder. Now this is important. If it finds a weed, it's sure that it's a weed, it is going to turn on the sprayer. Now this is a little bit, we'll get into how it turns on the sprayer in just a moment, but for now, this is the section of code that it says, yep, I found a weed, I am going to go turn on that sprayer for a second. Well, 700 milliseconds. And so as this drone is flying over the weed, it will turn on the sprayer and spray it. This is the second script here. This is actually we don't have a direct connection from Python to our sprayer on the drone. So what we actually do is we run this Python script in the Mission Planner tab. And Mission Planner is running an old version of Python. It can't do image processing natively there. So instead, we have to call a socket on our computer. And then what's highlighted here, the do command, is actually what turns on auxiliary 5 out on our sprayer, and then after 700 milliseconds turns off auxiliary 5. So what that has the effect of is it turns on the sprayer just for 700 milliseconds on the drone. Now, just a little bit more about how this works. Because I mentioned Mission Planner can't run a new enough version of Python to actually do image processing natively, what we do here is run the script in the tab as you see here, and all it does is sit and listens to a particular socket on our computer. It's in a loop there, just listening on that socket. And then the sprayer loop program that we have that's actually running a newer version of Python will turn on that same socket if it thinks that it found a weed. This is a bit of a klooge. Another reason that it's really not a great idea to run this version of code if you can get your hands on a Raspberry Pi Zero 2. Those are $15, you'll do better, and it can actually process the images right there on the drone with way clearer images and turn on the sprayer itself. But if you want to go with this, this is how you have to do it. So you would first run your sprayer loop, then you would turn on this listener in Mission Planner, and all it would do is turn on the socket on your computer when it sees a drone, when it sees a weed, and then Mission Planner would send out the signal to auxiliary 5 and actually turn it on for your drone. Great job. You've now got a drone that can fly, it can identify what's below it, and it can spray it as needed. This was a huge project. Thank you for following me this far. If you're really interested in doing more of this, you probably made it this far, so you are. Contact me in the comments and we'll meet up outside of YouTube. Now, one more thing. This is the disclaimer, and it's the oversight disclaimer. In order to do this, you need to have a Section 107 pilot's license for your drone. Here's the page that you need to go to. You can learn more about it right here. You do have to pass an FAA certified drone pilot test. So that's like $160 to get that test and do it. And then once you are a certified pilot, you have to essentially register as a crop duster and then ask for exceptions. So Section 137 and Section 107 of the FAA code says that for drones that are less than 55 pounds, you're allowed to fly this stuff, you're allowed to do this, but because you're going to be spraying herbicide or pesticide or whatever, you have to get some exceptions from 137. Here it is. It says that you have to have a pilot in the thing. Section 137 41C there says you need a pilot. Well, we don't have a pilot. This is a drone. And then Section 107 says you can't have poisons flying in anything unless you get a permit. So since we're going to be in a drone and spraying this stuff, we need a 107 and a 137 exception to do this legally. Now, I actually only have the 107 pilot's license right now. I do not have 137 and 107 exceptions yet. I'm working on it. So right now, I'm spraying colored water just so that I can see that it actually sprays, my blackberries like I want. I can't spray herbicides on them yet. But at least the system works, and I know that I can fill it up with herbicide once I get those. So how do you actually go out and get that exception? This is the page that you need to go to. There's actually good examples of others that have gotten exceptions. You can follow their formatting right there, and just follow the wording that they've got already out there. It does take a lot of time, but it's doable, and you need to do this to be legal. So there it is, a do-it-yourself autonomous intelligent ag sprayer drone for $1,000. Be sure to check out the bill of materials and the schematics down below. Let me know what you think in the comments, and don't forget to like and subscribe for more unique and useful do-it-yourself builds.